It's a pleasure to introduce Kevin Schreve, who is from here, and he'll be talking about homology in towers, or maybe in covers that are more general than towers. Well, he'll talk about what he will talk about. Okay.
I'll talk about something maybe related to the title, right? Okay, thanks, Shmuel. Thanks, everyone, for coming. So I'm just going to get started. Yeah, I felt bad because, like, the last talk in this colloquium started like 2,000 years ago and had like math on stone tablets, and there won't be anything like that. I'm just gonna tell you what the setup is, and then we're gonna play this game, hopefully. Okay, so here's what we're interested in. Sorry, so I have to like slightly control this. We're gonna start with some simplicial complex, some space, and we're gonna have a lot of finite covers on this space. So the way that we, assure that our space has lots of interesting finite covers is we put this restriction on the fundamental group of the space. Okay, so what you say is that the fundamental group has to be residually finite. It means that there's a lot of finite index subgroups, and those will correspond to a lot of finite covers. So in particular, we can find this tower of coverings where we have, so I should have said, well, I did say nested, okay. So these subgroups, gamma k is, contains gamma k plus 1. They're all normal subgroups of the group, and they all intersect, and they intersect trivially, okay. So going to covers of the space X, what this leads to is regular covers that are getting larger and larger, and in some sense limiting to the universal cover. In the sense that if you're a point living on this cover, it's harder and harder to tell, that you're not just in the universal cover. Okay, and then the game you play is you take your favorite invariant that you like. I listed some here that I like. There's others that you could be interested in. For this talk, I'm mainly going to do the first two. So you can look at like a Betty number with some field coefficients. You can look at torsion in integral homology, or take minimal number of genders of the fundamental group. These have all the advantage of just being numbers, so it's like slightly simpler when you want to take like a limit of these. In any case, you take a cover, you take these larger covers, and you see how this invariance grow. And usually what happens is you'll end up normalizing in some way so that you hopefully limit towards something interesting. Okay, and then if the game is successful, if you're happy, you get some things. So first, you hope that these invariants limit to something. So in the case of numbers, I can just say I want my numbers to converge. What's good if you want to kind of get an interesting limit is that the number shouldn't depend on the sequence of finite covers that you take. And hopefully, I mean, what turns out in the cases where all of this works, what happens is you get some sort of L2 or invariant of the universal cover. So there's an invariant with some kind of analytic flavor to it at the end. Okay. So here's like okay, so I'm gonna, scroll up like this, some places where this occurs. So in the first case, sometimes it's just a difficult problem to figure out if you have any non-trivial growth at all, okay? So for example, it was kind of a long, hard problem. I know it was on Thurston's list of like problems about 3 manifolds in the early 80s. Someone can shout out, who actually originally asked this. I don't know if it was like due to Waldhausen or. In any case, this is when I saw Benson here. I was hoping he would just, yell out the answer. But
it's correct. It's correct.
Okay, that's when it first. Okay, so. So this was just, solved decently recently by Agel in 2012, and this, which in his work, which led to a lot of the these problems with Thurston being answered. So the question was just, can you get started in this game? Can you find a finite cover with any non-trivial Betti number? Okay. So anyway, so it turns out that's hard. What you kind of hope is that if you can play this game correctly, then the invariant upstairs will give you a lot of growth downstairs. And that kind of works here, but it turns out the invariant ends up being trivial. So it wasn't, so it still needed Workavagal. Okay, so also what can occur is that, well, computations show, and there are kind of precise conjectures, which tell you that if you look at congruence covers in arithmetic groups, you expect a lot of torsion. Okay, so there's, you can, and people know kind of where for what groups you kind of expect this large torsion growth and what dimension you're expected to see it. So I'll talk a little bit about this later, but also, I'm also one of the people who doesn't know much about cohomology of arithmetic groups. And one of the things that I kind of that will hopefully come across later is that there are going to be other groups which are interesting, but you can actually get your hands dirty and really make, solid computations. Okay, so often the problem is if you're trying to study the growth of these invariants, it's just it's hard to get precise answers. It will turn out that there are going to be some groups which you can have precise answers and still get something kind of, interesting out of it. Okay, so I can't go very far in talking about growth without telling you about the case where this game just works completely. Okay, so this was the Theorem of Luke. In the 90s, it was, I think, asked by Gromov, maybe earlier also, in the 80s. So it says that this game works very well if you look at rational Betti numbers and you normalize by the index, okay? So in the first case, you get that if you look at the rational homology growth and it's normalized, you get that it converges to something. Okay, so I can put a limit there. That's nice and also not obvious. It turns out it doesn't depend on the sequence, and the number that you get is interesting. It's the L2 Betti number of the universal cover, okay? So I'm going to actually tell you a little bit about the right-hand side in a second, but I'll probably say this without thinking about it later, so I had to write it down, that when I say like the words FP L2 Betti number, what I mean is just measuring the FP homology growth. So it's exactly analogous to this Theorem of Luke, just with FP coefficients rather than rational coefficients, except that less is known. So we don't know whether these numbers converge in the finite field case, and we don't know it depends on the choice of sequence. So it's just kind of a lot of stuff is unknown. So maybe I should say here, see, I was hoping I could write here. So I was hoping I could write. So there's a couple cases where if you take these finite covers, you do know more. So for example, if you look at, oh, I was writing with my eraser, sorry. So if you look at P to the N index covers, this is slightly better, okay? Because it turns out these numbers are monotonically decreasing, and so you do actually, get a limit in the end. Okay, so that's nice. And then you can choose nicer covers, which was considered by Caligari and Emerton. So these are special towers coming from congruence covers and p-adics. And in that case, they can say a lot more, okay? So you do get a lot of information. So in particular, like a very natural question to ask is, okay, so this number is 0. Like, let's just say my, growth is sublinear for FP homology. Well, what is do I have, can I still say something? It turns out that you still can say something about like the precise amount of torsion growth or FP homology growth. So it turns out to be like a lot in a lot of cases, but sublinear. So anyways, I'm going to omit it because just sheer ignorance on my part. Okay. Okay, so what I'd like to do now, so I want to I told you Luke's approximation theorem. I want to just say if I have a lot of homology, so if like my left-hand side of this equation is non-zero, like can I produce anything on the universal cover? Okay, like should there be any reason why this is true? So I'm going to tell you kind of a weak version of what's called Kazhdan inequality. So maybe I should have said, if I write this is due to Kazhdan. Okay, proved much earlier than Luke. And I'm going to tell you even something weaker than what he showed. Okay, so here is what you do. So you suppose you have a group, you have a sequence, you know that you have a decent amount of homology in this residual cover. Okay, you want to produce something on the universal cover. Well, the first thing we can do, I guess I switched to real coefficients because I want to talk about this harmonic chains. You can identify the space of homology just with real coefficients with the subspace of harmonic chains. So every homology class is going to have a harmonic representative. This is just, in my world, this is combinatorial analog of Hodge decomposition. Okay? So the space of homology classes, I can identify with kernel of this combinatorial Laplacian operator. So, I mean here, okay, I'm looking at boundaries. The delta should probably be adjoint of boundary. If you identify chains and cochains, then this is just the co-boundary operator. So you're looking at kernel of this, and it says that there is a decent proportion of such classes. Okay, so I have a lot of homology that gives me a lot of harmonic classes. Okay, and then, so therefore what I have is roughly, so I think I wanted to kind of make the numbers, there was too many letters and numbers. So I'm assuming that it was around 1. So the J is supposed to be the index, and D is fixed. It's roughly the number of cells of X. Okay, so this R to the JD is just the dimension of the chains, and I'm assuming that the lim sup is like pretty close to 1. So I get roughly a J-dimensional subspace. I should probably have an epsilon in there, but I didn't want to do that. Okay, so what we have is a sequence of covers as we go up the tower, and we know that there is kind of a positive proportion of these chains which are harmonic. Okay, what you want to do from this is say that somehow these harmonic chains limit to something in the universal cover, limit to a harmonic chain. And so what you can worry about here, so maybe I'll just draw a picture. If you do this for a circle, so here's some kind of cover of a circle. Okay. So I want the harmonic chains to limit to something. So I should probably assume that they have like bounded norm. But that means on the circle, I'm just looking at constants, and therefore the values that I associate to every edge should be the value should be going down. Okay. So in the limit, if I take the limit of these harmonic chains, one chains, I guess, they'll limit to just the 0 harmonic chain on the universal cover. Okay. And now what I want to say is if I have something like a wedge of 2 circles where my covers now, if I take a finite cover, it's getting much larger, I should be able to find something on the universal cover which these limit to and also is non-trivial. Okay. So let me tell you kind of the main idea, which is just, it's a lemma from linear algebra, and I provided the proof because, it's a linear algebra proof, so it's nice. So it says if I take a reasonably large subspace, so making up a positive proportion of R to the D, there's a unit vector with a reasonably large coordinate. Okay. And the proof is you just project to that subspace. I know what the trace of that projection matrix is. It's just, the dimension of the subspace. And there's JD diagonal entries. So one of them has to be bigger than or equal to 1 over D. And then just take the vector containing that one. Okay, that will have norm less than or equal to 1, and it has a reasonably large coordinate. Okay, so therefore, what you can do now is you go to your finite cover, translating this back into our setting. You can, inside the chains of this finite cover, you find a harmonic chain which has L2 norm 1, and the value on a simplex is reasonably large. Okay? And if you're still with me, or you're leagues ahead of me, what you might worry about now is that these finite covers are getting larger and larger, but the large value is tending off to infinity. Okay, and then when you limit to the universal cover, you still get something which is trivial. Okay, and this is where you use the fact that these covers are regular. So there's a finite group action which allows you to take that large value on this chain, move the large value back to some fixed fundamental domain, and then you just see that persisting through the tower, and it limits to something non-trivial. Okay, so when you take the right translit back to this fundamental domain, these chains converge to something, which is going to just be, well, it's going to be harmonic. So meaning just define the same operator on the universal cover, just boundary and co-boundary. It's going to be non-trivial because that's exactly what we did to set this up, and it'll be square summable. I mean, you'll have L2 norm 1. Okay, so this space of non-trivial harmonic square summable chains is exactly what the L2 Betti numbers of X measure. Okay. So I knew it was, so I thought it was kind of dangerous to give like a proof in a talk or like in a colloquium talk. I hope that, so any questions on kind of the proof? I feel like somehow, it was elementary enough that I wanted to, that I thought people should see it. Okay, so let me just draw a picture of kind of what you kind of.
Well, it's sort of a cool proof because it tells you that the L2 cohomology on the universal cover, right, once it's non-zero, has to be infinite dimensional, right? Because this has a bump somewhere, so then you could translate that bump by any group element.
That's right.
Right? What I don't see yet immediately, but probably is true, is that there's a subgroup gamma prime of finite index in this gamma, such that all of those bumps are linearly independent and that you really see that there's a regular representation of some subgroup of finite index inside. Is that right? Or I don't instantaneously see it, but it looks.
So what you do, you see on the universal cover, you'll get, you get infinitely many
right.
from these just by translating by the group action. And then, is that what you want, or?
Well, I was asking whether you could get something a little bit more precise.
Oh, so you want something where all of them are linearly independent?
Yeah, but that's certainly not worth interrupting for, but you invited this, so.
Okay, let's think about that. I certainly invited the details, yeah. Okay, so that's the proof. I think it's kind of a beautiful way to show, that you have non-trivial growth in finite covers, right? So, that's what Luke, so this went one direction, and what Luke's approximation theorem tells you is if you want to find some sort of large growth, you don't have to work with finite covers. You can go to the universal cover and find a chain like this. And once you find a chain like this, then you're guaranteed to have, the linear amount of growth. Okay. So let me go on. So the next conjecture, so this is just, I kind of threw this in. So I wanted to say some conjectures for L2 Betti numbers. This one I threw in, it's kind of randomly, but I think it's a nice conjecture. So ITEA was the one who introduced these L2 methods in topology. And he, in his first paper, said, well, if G is torsion free, okay, then the L2 Betty numbers should be integers. Okay, so again, I haven't said what the L2 Betty numbers are. I kind of just said what they measure. It turns out you can associate to the space of harmonic chains a nice number, or you can just be content with using Luke's approximation theorem to define them. Okay. So what he did know, I mean, I don't think he thought about growth rates, but he did know that if I look at the L2 Betty numbers of the universal cover, I'm going and take the alternating sum, I'm going to spit out the Euler characteristic of X. Okay, so you can see that from kind of the real definition of L2 Betty numbers, or in growth rate, it's just immediate. Okay, so it's not crazy to think that the reason that these numbers sum to integer or sum to the Euler characteristic is just the fact that they're all integers. Okay. And anyway, so from the perspective of looking at growth rates, I think it just sounds crazy, but it turns out to be true for a lot of groups, though you don't prove it by looking at growth rates. Okay, so now I'm gonna not really be interested in spaces anymore, but I'm gonna be talking about homology growth of groups. Which means I'm just gonna be looking at the growth rate of classifying space for a certain group, and I'm gonna be looking at F2 L2 Betty numbers or torsion with rational or FP coefficients. Okay, so the other conjecture, which you can kind of, tell you how these growth rates are kind of conjecturally supposed to behave, is conjecture of Singer, who I'm sure didn't ask it for aspherical manifolds. I probably asked for closed non-positively curved, and it might also be. I'm just going to put Dojic here because it's attributed to Singer, but I think it's probably came up with by Dojic as well. So it says that if you are a manifold, a spherical manifold, then there should be zero or sublinear rational homology growth outside of the middle dimension, where you're kind of forced into it by Euler characteristic. Okay. So again, this has been confirmed for a lot of manifolds, like locally symmetric manifolds. In particular, all three manifolds. So for example, if you are in odd dimensions or in dimension 3, you should have zero rational homology growth. And this is why this doesn't help you with something like solving Thurston's question about virtual first positive Betty number. Okay, but still, this is kind of like what's expected. Okay, so let me talk about torsion again. So for torsion, there's no analog of Betty numbers. So instead, there's kind of various variants of this idea, but you can look at the torsion subgroup, just measure its size, and then instead of taking a Betty number, you take the log. Okay. Again, normalized by the index of the cover. So this example, yeah, so if we had like a number theorist give this talk, they could give you like beautiful examples about torsion in arithmetic groups. But you invited kind of you had like me talk, who's like kind of geometric group theorist, so you have to see the Baumsog solitaire group, okay, which I think is a good group. And I mean, this is mainly for my benefit because, well, oops. So now I have to turn this off. Okay. So, I mean, when I started thinking about torsion, I basically had, no idea how you could ever get in a finite cover, exponential torsion growth, but like, but bounded Betty numbers. Okay. But in these examples, you can easily see it. Okay. So so the bump-slug solitary groups defined by this presentation, just a better way to think of it is just as the fundamental group of this space, which is mapping torus of a circle. So this is like honestly a circle. And then you take the mapping torus of a degree 2 map, okay? And you can define BS-MN in kind of a similar way, okay? Just gluing on a cylinder with the degree M and degree N map. And then anytime you have a torus, you can, or anytime you have a mapping torus, you can unwrap that mapping torus. So you can just take the, instead of doing the map once, you do it n times. Okay, so this is now, this is a finite cover. I guess this is like times 3. And then generally you get the fundamental group being the bump-slug solitary group, but you just get n's instead of 2's. Okay? And now what happens is, okay, you just compute H1, and you see that inside here, well, I think there's a Z, and then you get a, well, okay. So inside here, there's a Z 2 to the n minus 1 Z. Okay, so you get this huge amount of torsion because the differential is now, 2 to the n. So the norm of the differential grows exponentially fast in these finite coverings. And now this is, so anyway, so that's, you get exponential torsion with growth, which I think is interesting. And you also get kind of interesting behavior, right? So this is like, 2 to the n minus 1 is conjecturally prime for, for maybe, I'm not sure if it's a conjecture, but it's unknown if you plug in infinitely many primes, whether this number is prime. In any case, you get kind of a large prime factors, or decently large prime factors of these numbers. So what happens is the torsion in these covers grows exponentially, even though the eddy numbers just stay constant. And if I look at like the prime factors, they're getting large and somehow summing up to something which gives you exponential torsion. So it's the kind of the downside of this example is that there's not that these covers are not residual, right? So the intersection of these subgroups is not trivial. So instead, but in any case, you're getting a lot of covers. You get some exponential growth. It turns out if you actually take finite index subgroups that that limit to the universal, or take these finite covers which limit to the universal cover, you'll get trivial torsion growth. Okay. You can do similar games with, like, instead of S1, you put hyperbolic surface, and you put a mapping torus of a 3 manifold, take the corresponding infinite cyclic covers. Again, you'll get exponential torsion. This was, I think, studied by Silver and Williams. But I think it was actually open whether you could get a group with exponential torsion growth in, in the setup that we had, residual towers that residual covers of groups. Okay, so
by the way, Kevin, just to be sure, here you're asking, can you find it, right? You don't know that the torsion growth is actually independent of the chain, right?
Yeah, I don't know that. For sure, that's
so you're asking about
so the question is there a finite index normal residual chain where this quantity is non-zero?
But it's still imaginable that the answer is independent of the chains, right?
Yeah, that's right.
Right, it used to be that was common wisdom, but now it's still just conceivable.
What? Yeah, I guess. Right.
Okay.
So it will turn out that we'll have examples, and it will turn out that the torsion doesn't depend on the chain. But you're right. It's certainly unknown in general.
Okay.
Okay, so one more example, again, where you kind of see lots of torsion, but without large Betty numbers. So these were examples considered by Dunfield and Thurston as kind of models for random 3 manifolds. So what you can do is you can take 2 handle bodies of the same genus and make a 3 manifold by gluing them with some homeomorphism. Okay, and what they did was they started taking very complicated elements of the mapping class group and study their, the topological behavior of these manifolds. Okay. In particular, you can ask what happens to the first homology group. And it turns out for a kind of generic F or sufficiently complicated F, the probability that the homology group is finite, so that there's no rational Betty numbers, is 1. So generically, these should have finite H1. You essentially can see this from, well, you can write the homology of this resulting 3 manifold is basically the homology of the surface, of the boundary surface, modulo like 2 subspaces of half the dimension. Okay, and so it turns out, and generically for generic F, these subspaces span, and so you get finite first homology. But what they also checked is, well, they wrote down the precise probability, but if you have a large prime and you again ask for kind of what happens in the generic case, it turns out that homology with these FP coefficients is supposed to be non-trivial. Again, it's kind of, I mean, you're saying these subspaces are kind of equally distributed, but now there's only finitely many subspaces because you have FP coefficients. And so you expect sometimes that you get some homology. They don't span. And so what happens is you get large homology of this group, I mean, for, large primes, but again, no rational growth. Okay. All right, so let me go to the next slide. So the first, so this first conjecture about FP homology was in a survey of Luke a couple years ago. It will turn out, so I'm not sure if Luke, thought that this was true or whether he was just trying to say this is, in general, it's difficult to know the FP, to work out the FP homology growth. So it was open whether, in this setting, whether FP homology growth was the same as just rational homology growth. Okay. So maybe I put, okay, this is just universal coefficient theorem. But so the question is whether you get kind of more FP than rational homology growth. It's pretty easy to come up with spaces. I mean, very easy to come up with spaces where this is true. And it's also easy to come up with like finite where these covers aren't residual where it's true, but in general for normal residual covers, it was open. Okay, the main point where I started thinking about this stuff was there are going to be examples that I'll show soon where this conjecture is false. Okay, so you get more FP homology growth than rational. So the other conjecture is kind of telling you what's expected to happen for torsion. You can think of it as an analog of Singer conjecture about rational homology growth, but now for the torsion. So it says you take a closed aspherical manifold. If you're not in this degree, which will turn, so for odd, in this case, for even dimensional manifolds, you're just supposed to see rational homology growth in the middle dimension and trivial torsion growth everywhere, or not, well, sub-exponential. In odd dimensional manifolds, you're supposed to see vanishing of torsion growth, except in this middle dimension for torsion, where it's supposed to limit to something, okay? So the thing on the right is the L2 torsion of the manifold. So maybe I'll just, I won't really describe it too much, but you can work out for certain cases that this is, non-zero, and you can compute it. So maybe I'll just say this part on the right, or left, I guess. So this growth of torsion, you can think of it as coming from two places, okay? So it comes from looking at the spectrum of the Laplacian on these finite covers, okay? So just, you want to work out what the eigenvalues of the Laplacian are on the finite covers. And then there's these other terms called regulators, which tell you something about how the integral homology is sitting inside the real homology. So for if this was a Riemannian manifold and I was doing things analytically, this would be the Cheeger-Muller theorem, which says that, well, that there's the analytic torsion coming from spectrum of Laplacian and regulators, and that tells you size of the torsion subgroup. And this part is basically an analog of the first component. So it only cares about the spectrum of the Laplacian now on the universal cover. So in some sense, it's saying two things. Like, it's saying there's an approximation of these determinants, like the Laplacians downstairs are supposed to limit to the Laplacian upstairs, and this regulator term is supposed to not contribute in the limit. Okay. So this conjecture was really motivated by number theory. So it's a generalization of a conjecture of Bergeron and Venkatesh. They asked it for arithmetic groups and congruence chains. And so Luke is saying, maybe this is a fact about aspherical manifolds. So if you look at it, for example, and this is just, I think, kind of a beautiful story, if you have like an arithmetic hyperbolic 3 manifold, actually, I think in this case, it's conjectured to hold for all hyperbolic 3 manifolds and normal covers. But if you take one with congruent subgroups, then the conjectured torsion growth, so here, yeah, I'm not sure why I did this. So the L2 torsion is like the volume of the manifold times 1/6 pi. So here, this is secretly has like the index of the cover. I just, divided both sides by the volume of the manifold. In any case, we're supposed to get kind of a large amount of torsion, even though conjecturally, again, the FP homology growth is supposed to vanish for all P. So it's similar in some sense to Baum-Fleck-Solitar groups in that you're not supposed to have a lot of FP homology for all primes, but you're supposed to have large primes that combine to give you this non-zero growth. There's also conjectures about SL3Z, other Bianchi groups. So you can also, there are also things you can say for non-compact manifolds. Let me see. So in this case, for the hyperbolic 3 manifold setting, at least, you do have some version of this Cos-John inequality before. So we know that 1/6 pi is like an upper bound for what this torsion growth can be. But I think this is right. People can tell me if I'm wrong. That there's no known examples so far of just like you take a hyperbolic 3 manifold, you look at any sequence of finite index covers, and you just want to see non-zero torsion growth, or exponential torsion growth. So there's supposed to be a lot, and people can do computations in the setting of congruent subgroups and show that there's a ton, but in these finite covers, but in the limit, you don't know if this persists. Okay, let's see. Questions about this or comments? Okay, so let me tell you some theorems now. I should have said this at the beginning. So everything I say, is going to be based off joint work with Grigori Abramidi and Boris Okun. So the first thing we say is that we can find groups where we can actually compute things, and you get more, so this is strictly greater, you get more FP homology than rational homology. And if you want large torsion growth, so if you want to find finite covers where you get, exponential amount of torsion, you can now do it by just taking, essentially from universal coefficients. So once you have a linear amount of FP homology and not much rational homology, that's what you're guaranteed that. The other thing that we can do is construct manifolds, which give you, which contradict kind of an FP analog of Singer conjecture. Okay, so there's going to be some odd dimensional manifolds with non-trivial FP homology growth, and you can also get even dimensional ones outside where the growth is outside of the middle dimension. Okay, except that we can't do this for, we can only do this for odd primes. Okay. So what happens is now you kind of, so you prove this and you look at, you've disproved an FP version of Singer, and then we realize, well, it turns out that if you take the original Singer conjecture and then this Luke's conjecture about vanishing of torsion growth, together they imply an FP version of Singer conjecture. Okay, so that means that one of these, for these examples that we construct, one of them has to be false. So as you say, I mean, I guess, yeah. So either you get something with non-trivial rational homology growth, or you get something with torsion outside of this middle dimension for torsion. Okay, so I want to tell you how you compute. I'll tell you what the groups are, and then I want to tell you, how we compute the FP homology growth. Okay. So let me warm up and just tell you how you would. Okay, so I'm going to try to move this down a little. How you would compute the FP L2 Betty numbers for free groups. Okay, so I know that you can that we can use Euler characteristic. That's a perfectly good proof. But I want to do kind of a slightly more convoluted proof, and which will hopefully help later. Okay, so here's how you would show that there's compute the FP homology of a finite cover of a free group. Well, first I take this kind of like funny model. I don't take a wedge of two circles. I take two circles and I cone off I cone off 2 points. Okay, that's just going to be my model for a KF21. Okay, then I take a finite cover and it looks something like this. Okay, so the circles are going to unwind a bit, presumably. I mean, and we know that in the limit, what's going to happen as I take larger and larger covers, all of these circles are going to unwind. Okay. Then what I can do, I'm just filling in my missed cone points. So what I can do then is I can remove the cone points and recellulate the circles to just have one vertex and one edge. So I know in this finite cover, there's going to be a sublinear number of lifts of of each of these circles. Okay, so here I see something which is where there's a sublinear number of cells. I mean, I didn't really have to remove the cone points. I could have just, started moving all these circles around, or, kind of squashing everything down to this picture, but somehow I understand it better here. Okay, so we've removed the cone points, we get sublinear number of cells. I mean, that essentially corresponds to the fact that these circles do have to totally unwind in these finite covers. So what I know is that the homology here at this point is trivial. And then I glue everything back in. So I guess these are my cone points. Okay, and I glue in a linear number of cone points back in. So I get some picture which looks like this. And the good news is I don't really have to understand how I reglue everything. Because what I have is a sublinear number of circles. I'm gluing in a linear number of edges along S0s. So I'm going to see a linear number of first homology come up in some Meyerbeer-Torres sequence. Okay, so that's the point. We don't really have to understand anything. You just see something sublinear, and then you see something, and then you're gluing in something linear. Okay, and the good thing about our groups is that the same thing works for them. So the groups that we kind of start, that we can compute with, are called right-angled Artin groups. They're good examples in geometric group theory because they're easy to construct. They have a lot of structure, but you get some sort of flexibility in their construction. So instead, you can think of, I should have done this one. So L is 2 points, and that produces for you the example we had before. Okay, so you get the free group. In general, you take a simplicial complex and you make a space where you just take a torus for every of the right dimension for every simplex, and then you glue them together along subtori corresponding to simplices in your space. So in this case, for every vertex, you put a circle. For every edge, you put a torus. And then if you see two edges intersecting in a vertex, you glue the corresponding circle, you glue the corresponding tori together along that circle. So there's kind of a canonical way to construct KG1s for these groups just by doing the right definition of how to glue these tori together. The one thing you have to do, so here, I would do the same thing. So I tried to draw L being a circle. You do the same thing. You put tori at every edge. You put circles at every vertex. You just glue them, identify the tori in the standard way. And then the one thing you have to do, and this is why I ended up doing this for the wedge of 2 circles, is you have to cone off a copy of L inside. This is to guarantee either that you have the right fundamental group, or in general, if I'm looking at something like a sphere, like if L was some triangulation of a sphere and I just put tori everywhere, then I would see this sphere and I wouldn't get a spherical thing. Okay, so you have to end up, if you want to build a classifying space for your group, you cone off kind of any interesting topology that you see in L. But the good news is that the same proof that I gave you before works for these groups. Okay, so the proof is you take a finite cover. There's going to be kind of 2 parts to it. There's going to be a linear number of lifts of this coned off copy of L. And then there's this cover of the things that cover this subcomplex, which consists of just tori. Okay. And the tori you can again recellulate so that there's no so that the cell growth is sublinear. So I don't know, I can't draw a good picture anymore. So you have a bunch of tori in this finite cover, which you then replace with kind of standardly cellulated tori. You get a sublinear growth of cells. So you get trivial FP homology, or trivial, all homology will be trivial. And then you again cone off a linear number of copies. But in this case, you're coning off a linear number of copies of L. Okay. So what you see is just some kind of acyclic thing, and then a linear number of copies of L coned off. So what you end up with is just the FP homology growth is just a linear number of copies of cone L rel L, okay, which is easy to compute. Okay, so that's our theorem, one of our theorems. So it says that if you take the mod P homology growth or even or rational homology growth of these right-angled Artin groups, what you get is exactly the L and or the homology groups of L with those same coefficients. Okay, so we take things like L being a flag triangulation of RP2 to get something interesting. Okay, so at least you get more F2 homology growth than rational homology growth. Wait, so maybe I should ask, I guess I didn't realize this. Is this supposed to be 50 minutes or 60?
Between them. I mean, it depends on interruptions and questions and stuff like that.
Okay, so maybe I'll just say a couple more things then. So one more thing that we can do is compute the torsion of we can also compute the torsion growth of these groups. It will turn out to be independent of the chain, and it's kind of exactly what you expect. So if the homology of this group is just the homology of the complex, the torsion growth of the group is going to be the torsion of the complex. Okay, so again, it's the same, essentially the same proof. You see just a linear number of copies of L coned off. What's trickier in this case is showing vanishing of this chopped complex. So you can't just use a sublinear number of cells anymore to kind of compute things, because you have to worry about the differentials being controlled after you recellulate. Okay, so this is kind of, similar to the problem for Baum-Select Solitar groups. You can recellulate things so that it has very few number of cells, but the differentials blow up. So you have to show here that the differentials don't blow up. Okay, so maybe I'll just say how you kind of make a manifold out of this. So you start with a group which has more rational homology than FP homology. Okay, we have to take it to be something like a Moore space for, well, so you could take something like RP2. It'll turn out that 2 is no good though. So you want to take something like a space with more Z3 homology than rational homology. It turns out this, so by the formula, this will have a lot of kind of Betty 4, so there will be a lot of 4-dimensional FP homology growth. And then kind of the main trick, which requires the fact that you have an odd prime, is that you can make this group act on a contractible 7 manifold. Okay. So this is actually, I mean, the way that this all came about was we were trying originally to disprove Singer conjecture using these right-angled Artin groups. And you can compute the rational homology growth in the same way, and you'd be done if you could get these groups to show, if you could show that these groups somehow acted on a contractible 7 manifold properly, but we showed that they can't act properly on a contractible 7 manifold. So this strategy that we had for disproving Singer failed, but then it turned out that it kind of worked for odd primes. Okay. We don't know if the prime 2 is kind of important at all. And then finally, there's this kind of trick where you can turn a proper action into a proper co-compact action of some different group, and then you get that this FP homology growth still survives. So that's how we get our examples of manifolds. Okay, so I think that's all I had. So I had some fun with the iPad, so thank you.